In this video, I will show you how to use the chain rule to find the equation of a tangent line at a given point. For number 76, we are to find an equation of the tangent line to the graph of f at the point 1, 4. As soon as they ask us to find the equation of a line, we're thinking, let's use point slope form. So that means we need two things, a point and the slope. But when they gave us the point of tangency, they gave us the point that we can use for the equation. So all we really need is the slope. So of course that means we need to find the derivative, which will be a slope-making machine. Before I find the derivative, I'm going to just sort of colorize this for the chain rule. So you can easily see that we have the outer function here in blue, and then the inner function here in purple. So according to the chain rule, first we're going to take the derivative of the outer function. So I'm going to put the 2/3 in the front, and I need to reduce this power by 1, which means I'm really subtracting 3/3. So that's going to be negative 1/3. So I have the negative 1/3 power. So I've taken the derivative of the outer function. So I leave this inner part alone, but then I multiply by the derivative of the inner function. So using the power rule, the 2 comes to the front here, so that's going to be negative 2x. So this is the derivative. Let's use this to find the slope. We need to find the slope at the point of tangency. The important part is the x value. So we need to find the slope at 1. So that's why I am evaluating the derivative at 1. So let's just simplify this a little bit. So we've got 2/3. This is just 1, so 9 minus 1, so we've got 8 to the negative 1/3 power times negative 2. Because of the negative 1/3 power, this is going to end up being dropped down to the denominator. So this would be 8 to the 1/3 power in the denominator, but the 1/3 power is the same as the cube root. So I'm actually going to write it that way just so you can remember that we are talking about the cube root of 8. So meanwhile, you see this 2/3. So the 2 is going to end up in the numerator and the 3 is in the denominator. But wait a minute, what about this negative 2? So really the negative 2 is going to multiply by this 2. So in the numerator, I'm going to go ahead and put a negative 4 actually. So we have this. How much space do I have? I think I'm just going to go ahead and calculate from here. The cube root of 8 is 2. So this is going to be negative 4/3 times 2. So let me just squeeze this in. So the slope is going to be negative 4/6, which is the same as negative 2/3. So we had a point, we needed the slope. We just found that the slope is negative 2/3. Now it's time to use point slope form to write the equation of this tangent line. So we are going to write y minus y1, so y minus 4, is equal to the slope, so negative 2/3, times x minus x1. So x minus 1. And that's it. This is the equation of the tangent line at the point 1, 4. Let's do this again. We are looking for the equation of a tangent line to this function at the point pi/4, 2. So if we want the equation of a line, we will need a point and the slope. They already gave us the point, so all we need is the slope. If we want the slope, we're going to find the derivative, which will give us the slope at any point, including this one. But before we take the derivative, I'm going to rewrite this a little bit so it's a little bit more obvious what is the outer function and what is the inner function. So there's my 2, but you need to understand that if you have tangent cubed x, this is the same thing as having the cube on the outside and the tangent of x on the inside. This is just what tangent cubed x means. It's the entire tangent being cubed. So that makes this blue part the outer function, and the purple tangent x is the inner function. So now we are ready to do the chain rule. So y prime, we take the derivative of the outer function first. So I'm doing the 3 times 2, which is the power rule. So I will get 6. Reduce this by 1. Okay, so I just took the derivative of the outer function. I leave, whoops, I want this to be purple, man. You gotta color coordinate this stuff. So you leave the inner function alone, but then you multiply by the derivative of the inner function. And we have memorized that the derivative of tangent is secant squared. So this right here is the derivative. So if we want the slope at x equals pi over 4, all right, of course I'm getting the pi over 4 from the x value of the point of tangency, then that slope is going to be the value of the derivative at pi over 4. So I'm going to go ahead and put tangent of pi over 4 squared times the secant squared pi over 4. So hopefully you have memorized that the tangent of pi over 4 is 1. So this is going to give me 6 times 1 squared times. Now what about the secant of pi over 4? Remember that secant is the reciprocal of cosine. Maybe I'll do this off to the side. So what is the cosine of pi over 4? Some people say radical 2 over 2, but another version of that is 1 over radical 2. So the cosine of pi over 4 is 1 over radical 2. Secant is the reciprocal of this. So that means that the secant of pi over 4 is radical 2. See why I like doing 1 over radical 2? So when I do the reciprocal, it's simpler. But then we have the secant squared. So this is actually going to be, so the secant squared of pi over 4, if you square this, you're just going to get a 2. So that's what we're going to have from this. The value of that whole expression is 2. Kabam! So that means that the slope is going to equal 6 times 2, which is 12. So that's it. We have a point and we have the slope. That's all we need to write the equation of the tangent in point-slope form, because we will do y minus y1, so we have y minus 2, is equal to the slope times x minus x1, so x minus pi over 4. So that's it. This is the equation of the tangent line at the point pi over 4, comma 2. Last one. Determine the points at which the graph of this function has a horizontal tangent. Horizontal tangent means that the slope is equal to 0, which means that the derivative is equal to 0. So we need to find the derivative, set it equal to 0, and solve. This would be a good time to use the quotient rule. Plus, that gives me another opportunity to say the quotient rule poem, which goes like this. Low D high, less high D low. Draw the line and down below, the bottom squared will go. Let's go through it again. When I say D high, I'm talking about the derivative of the top part. So low D high. Low means just write down the bottom part the way it is. So I'm going to have radical 2x minus 1. You know what? Maybe I'll use the fractional exponent version. So radical 2x minus 1, I'll just write it as 2x minus 1 to the 1/2 power. So that's low. Low D high. So the derivative of the top part is 1, which I really don't need to write, but just for instructional purposes, there you go. So it's low D high less high D low. So I just write the top part, so that's high, and then D low. So I need to take the derivative of this bottom function. So we need to do the chain rule as I take the derivative of this bottom part. So remember, this is 2x minus 1 to the 1/2 power, and then the inner part will come next. So as I take the derivative of this, I start with the outer function, the 1/2 power. So this 1/2 power is going to come to the front, and then I reduce the power by 1. So it's like I'm subtracting 2 over 2. So that's going to give me the negative 1/2 power. So there I've taken the derivative of the outer function. At this level, the inner part stays the same. But then, because of the chain rule, you multiply by the derivative of the inner function. The derivative of this is just 2. Okay, so all of this is D low. So this is low D high less high D low. Draw the line and down below. The bottom squared will go. But if you square a radical, the radical goes away. So if I simply write 2x minus 1, that's actually the bottom squared. So look it over one more time. Low D high less high D low. Draw the line and down below. The bottom squared will go. So this is the derivative. But we are trying to find the equation of a horizontal tangent line. So we need to somehow set this equal to 0. So for the next phase of this problem, I am setting this derivative equal to 0. But when you set a fraction equal to 0, the only way a fraction can equal 0 is if the numerator is equal to 0. So when you set a fraction equal to 0 and solve, all you have to do is set the numerator equal to 0. You can ignore the denominator. The denominator can't be 0. It has nothing to do with it. As I set this numerator equal to 0, I am going to simplify it slightly. Obviously, I'm not going to write this little 1 here, but also we have 1/2 times 2. That's just 1. So those are going to cancel each other out. So I'm going to have 2x minus 1 to the 1/2 power minus x times 2x minus 1 to the negative 1/2 power. And like I said, we're setting that equal to 0, and we're going to solve. In order to solve this, we need to factor this. Notice that we have a common factor here. We have a 2x minus 1 here, and we have a 2x minus 1 here. So this is going to involve some next level factoring. So focus and get ready. We need to take the 2x minus 1 and put it outside of the parentheses. But we need to know what exponent should be here. And you go with the lower exponent. You always pull out the smallest exponent that you see. So that's going to be negative 1/2 power. So I'm factoring out 2x minus 1 to the negative 1/2 power. When you factor something out, to figure out what goes inside the parentheses left over, you divide by whatever you just factored out. When you divide by something that has an exponent, you actually subtract the exponent. And you know this. If I have x to the 6th power, for example, if I want to divide by x to the 3rd power, is this going to be x to the 2nd power because 6 divided by 3 is 2? No. You know that you subtract these powers, so you get x to the 3rd power. So that's what's happening right now. I'm dividing by this, so I need to subtract negative 1/2 from each of these exponents. So just be very careful. So I am subtracting negative 1/2. All right? I'm subtracting negative 1/2. When you subtract a negative number, though, that's addition. So really, I am indirectly adding 1/2 to both of these. So for this first one, I'm going to end up with 1/2 plus 1/2. So that's 1. So that's why inside of here, I'm going to have 2x minus 1 to the 1 power. So of course, I don't need the 1 power or even the parentheses at that point. So now the rest. So I'm going to have this minus x. Okay, that x is still there. But then I have negative 1/2 plus 1/2. So that's going to be the 0 power. So if I were very silly, I would write 2x minus 1 to the 0 power. But you know that anything to the 0 power is 1. So we're not going to write that. So really, we just have this. So I'm just going to space this out a little bit more. Okay, so we still have the minus x, but then this turned out to just be 1 because of the 0 power. So we did not need to write that. So that was our next level factoring. So we factored out the 2x minus 1, and we're left with this. Inside the second parentheses, this can be simplified a little bit more. So we have our 2x minus 1 to the negative 1/2 power, but 2x minus x is just x. So now I have x minus 1, and this equals 0. So 0 product property. We can set each of these factors equal to 0. I'm going to do a little shortcut on this one because pretty quickly you come up with the fact that it's really going to come down to 2x minus 1 equals 0. That's the only way that this expression can equal 0 is if the inside part is 0. So I'm just going to skip to that. And then I have x minus 1 is equal to 0. So adding 1 and dividing by 2, I get x equals 1/2. And adding 1 to both sides, I get x equals 1. So they said determine the points at which the graph of the function has a horizontal tangent. So when they just use the word point, that means we need the x value and the y value. So we need to do one more step off to the side over here. So we have found the x values, but we need the y values. For the y values, we have to go back to the original function. So we're going to say y is equal to x over the square root of 2x minus 1. That's the original function. Okay, but now we're going to find the y value that corresponds to each of these x values. So at x equals 1/2 and at x equals 1, okay, those are the x values we just found a moment ago, but we need to find the y values. So here we go. At x equals 1/2, we have 1/2 over the square root of 2 times 1/2 minus 1. Okay, I just plugged 1/2 in here and here. All right, I didn't leave myself a ton of space, but I think we can do it. So we have 1/2 up there in the numerator. Okay, 2 times 1/2 is 1. Uh-oh. Then we'll have 1 minus 1. So this is 0. So maybe I'll just show this in 2 steps. So we have the square root of 0, and this is in the denominator, you guys. So this has no solutions. So I'm just going to put no solution. Okay, so we can forget about this x value. So we will get no point from this x value. So our only hope is the other x value. So here we go. Y equals 1 over the square root of 2 times 1 minus 1. Just plugged in 1 for these x's. Let's see what happens. So we have 1 over the square root, and this is just 2 minus 1, which is 1. Of course, the square root of 1 is 1, so 1 over 1 is 1. So we have this x value and this y value. Put them together, and we get a single point, which is 1, 1. So this is the answer. This is the only point at which this function has a horizontal tangent line. That problem was so convoluted and crazy, I think it would be satisfying to take a look at Desmos and see what we really just did. So first of all, here's the original function that we were given. Supposedly, we found this point 1, 1, at which there would be a horizontal tangent line. So here's the point 1, 1. So if we look at the line y equals 1, we can see that this horizontal line is a tangent line at the point 1, 1. So that was a lot of crazy convoluted steps, but it did actually work.